I got a video request to do a video on graphing trigonometric functions and transformation. So you know who you are. Here it is. A quick stupid little thing. A moment of silence for this marker that was a great soldier and served in many battles, but now it's come to an end. Alright, so this video is going to have two parts. First part is graphing and second part is transformation. So the graphing part's on the left and then we're going to get into the transformations on the right. I'm not actually going to go through all of these functions to save you guys some time, but what I do want to, my main agenda here is to show you guys how you can figure out, and quote specifically, don't memorize, but how you can figure out how to do all of these. Alright, so let's get into it. I'm going to be making, so another quick note, this video is a little bit out of order, but I will put it into a sensible playlist later. I was going to cover this, but I did it sooner because it was a video request. Alright, so let's get into it. We're going to use the unit circle pretty heavily, so that's why I put it over here. So quick recap, the unit circle, this is a radius of 1, this x coordinate is cosine x, this y coordinate is sine x. So we're going to be using that a lot as we think about these functions. So a lot of you probably already know what the plots of sine x and cosine x look like. So let's look at those graphs. So here we're going to plot the angle, which we call x or theta, and here we will plot the value. So this will be the y coordinate. So, alright, let's see how we're going to do this. So first of all, notice that as we go around the circle, we're going to start repeating our values after 2 pi. So that's 360 degrees or 2 pi. So that means after 2 pi, whatever the plot looks, whatever this graph is going to look like is going to just duplicate. And if we're going backwards, it will duplicate again in the reverse direction. So let's say this thing looks like this. It's going to just be copy and paste left and right. Alright, so we're just going to do this once. Now let's see some interesting key values. So what is sine x when this angle theta is 0? So that means this height, this y coordinate is 0 over here. So at 0 it is 0. So again, we are plotting currently sine of x. Now let's see what happens when we increase the angle to pi over 2 or 90 degrees. So that's when the y is at the maximum, so it's 1. So that means if we want to get a 1, we have to be at pi over 2. That's over here. Now, and then the height decreases back to 0. So over here we have this point. So far we have these 3 points, and then the height's going to go to -1 over here, and that's going to be this point right here. So basically, what are we doing? First step is I'm getting the key points, which is 1, 2, 3, 4, 5 here. This point is actually the same as that point because we've just looped and we're back to the beginning. Alright, so now the question is, these are going to be connected somehow. Are these straight lines, curved lines? Now, you could just look this up, or if you don't even care, you could just memorize it, but I just want to show you how you can think, like a little trick to figure that out. Let's look at these angles. Let's say we're at 90 degrees. If you move from 90 a little bit downwards, so let's say this is like 60, notice the height hasn't dropped too much from this point to that point. So that means we are not moving linearly, so clearly this shouldn't be a straight line. Same thing here. If we go from 0 degrees to let's say like 30, we shoot up in height much faster than we did over here. So that tells you in the beginning we should be shooting up faster than at the end. So that's where this shape comes from, where it's curved like that. So this whole shape, which is this familiar sine wave, is coming from the fact that once you get close to 90, remember we said this height is not changing much from like let's say 80 to 90 degrees or 60 to 90. So that's why there's this slow down over here. We're curving this way. And you could trace that through each of these portions. So that's why the sine function looks the way it does. And if you want to keep going left and right, you would just do more of that like that way, and infinitely. Alright, that's the sine function. Now let's look at the cosine function. We don't have to retrace our steps too much. We just look at our critical points. So we have our pi, 2 pi, pi over 2, 3 pi over 2, 90, 180, 270, 360. So let's see what happens. When the angle is 0 degrees, the x-coordinate is 1. So we start over here actually. So as the angle hits 90, we reach the x-coordinate of 0, so we go here. As this angle goes to 180, the x-coordinate is -1. So we are over here, and so forth. So it's going to look like that and come up. So if you recall the sine function we just had, which looked like this, all the cosine function is a shifted version of that. So imagine if we shifted this another 90 degrees to the right, then this point would now become that point, and they would be the same. So that's kind of an important fact. So notice what we did. We applied the same reasoning to get cosine. So these are relatively simple compared to the others. So let's go to tangent. How would you get tangent? Well, let's think about tangent. Tangent is sine over cosine. So here's your x, here's your y coordinate. So let's think what happens. And again, I'm just going to look at our key points. There's a numerator and denominator. So let's just pick some nice angles like 0, 90, 180, 270, 360. When we're at 0, sine of 0, so that would be the y coordinate here, is 0. So we have 0 over 1. What is 0 over 1? That's just 0. So we are right here. Great. Now let's go to 90 degrees, where the height is 1, so that's going to be a 1. This coordinate, the x coordinate, will be a 0. So at 90 degrees, cosine of x is 0. So at 90 degrees, the tangent is going to approach 1 over 0 because the sine, or the y coordinate, will be 1 and cosine will be 0. So let's not go right to 90. Let's imagine we're like at 89 degrees. So we're almost at these numbers. So let's say this is like 0.9 and that's 0.1. The point is, this will start to get really huge. So imagine 1 over a really small number, let's say 0.00001, will actually blow it up and get it really huge. So what that means, we have to go from this point to something that's super huge. In fact, it's pretty much at infinity if you're actually at pi over 2. So that tells us how the curve should look. We can't go linearly because then we'll never hit an infinite point. We can't curve this way because then we're going to hit this wall. So we want to be curving this way. So that tells us the shape goes like that. And it's actually we're never going to get to this point because it's undefined, but it approaches this. So that tells us about this part. Now we could run this argument again, but I'm just going to say by symmetry, if you go left, what's going to happen is, so let's imagine now we are, instead of 0 degrees, now we're actually going to go to a negative angle. So at a negative angle, what is the y coordinate, or sine x? It is negative. However, the cosine, or the x coordinate, is positive. So that means we have a negative over a positive, which is negative. So that means this logic will repeat again. This is negative pi over 2, except it's going to curve this way because this time we're going to be going to this number. And if you don't quite go to the 0, let's say this is 0.0001, so right before we get here, we're approaching a really huge negative number. So this logic is reversed, but in the negative direction. So that tells you that's the tangent. And if you want to, if you're curious, like what happens if you're here, this is going to be copy and pasted because, like I said, we're going around the circle either forwards or backwards. So we'll just have this way and that. So this will just keep going that way. All right, so that's tangent. What I want you guys to get out of this is we're not using or memorizing crazy facts. We are just thinking things through, looking at special points, and seeing what happens as we approach things. So let's go to the next function, which is cosecant. So how would you, so first of all, cosecant x is 1 over sine. It's, I don't know why it starts with a c, but it makes you think of cosine, but just remember that this has to do with the sine. All right, so again, we're going to think about this the same way. Let's look at some interesting points. So this is your x, this is your y. So let's say x is 0 degrees, or your theta is 0 degrees. So 1 over 0, that's no good. So imagine we're not quite at 0, we're like at 0.1. So we're going to have 1 over 0.001, basically something really small, and like we said, that's huge. So what is this huge number? at 0 degrees, we are going to be somewhere off to infinity. So, okay, so we have something here. So this is basically going to be some interesting point. So let's try, instead of 0, let's go to 90. What happens at 90? Sine x is going to be 1 because the y coordinate is 1. 1 over 1 is 1. So at pi over 2, we are at 1. So we're going to keep plugging in these critical points, these special values. Let's say what happens over here. So as we go over here, we're going to have the same deal. The height is again 0 over here. So it's going to be 1 over 0, but this time it's actually the same thing, sorry. So it's going to be approaching 0, but from the positive side. So the height's going from 1 to 0. So again, if you try to go to pi, you will get something really huge. So like, let's say I'll just draw, this is actually at infinity, but I'll just draw it right here. And over here it's also at, point is not actually there, so it's at infinity. So what that tells us is when we go from here to in this direction or in that direction, we have to shoot up somehow. So using the same argument as before, we can't go this way, we can't curve this way, so that means we're curving this way because and these are actual points. We're just approaching these borderlines and we're getting closer and closer, but we'll never actually hit them. So that's it. That's the way cosecant x looks like in this interval. So then if you want to know what it looks like in another interval, let's say you're interested, what happens if you go to 3 pi over 2? So that means we are now not here, we are here. So what's happening? The y coordinate, so this is the y coordinate, sine x, so 1 over the y coordinate. The y coordinate is going from 0 to -1. So that means at this point we're supposed to get -1. So that's going to be over here. So we can run this logic again. As we go this way, the y coordinate is going from -1 to 0. So, but the key point is now, this is not the same 1 over 0 as we were getting before because we are approaching 0 from the negative side. So the height was negative and now slowly getting positive. So actually if you do 1 over sine x, the closer you get to 2 pi, the more it's going to go to negative infinity. So this is going to go this way. So imagine this curve is just going to go like that towards these borders. So it's all a matter of, are you approaching these borders from which side? From this side or that side? So if you're approaching from this side, it's going up to positive infinity. If you're approaching from this side, it's going to negative infinity. And then these two would just be copy and pasted over and over, left and right. So that's cosecant x. I'm not actually going to do all of these functions, but hopefully you're seeing what we're doing. We are choosing these sensible points, like 0, these nice points, 0, 90, 180, 270, and we're either getting these nice values or something at infinity, or like undefined. And if it's undefined, move off of it a little bit, and then you'll see, oh, okay, we have to approach something huge, so it has to curve this way or that way. All right, so that's basically how you figure out these plots. Now, let's go to, so I'm not going to do these last two, but you guys can do those on your own, or if you have questions, just leave a comment on those. So quick point on these arc functions. So these are inverse functions. Arcsin x is also notated this way. These mean the same thing. So when you see that -1, don't think this means 1 over sine x, which is actually a pretty sensible thing to think. That's just a bad math notation, but you'll see it a lot. So this has nothing to do with negative exponents. This is an inverse function, totally different. If you have questions, I'll be happy to say more about that in the comments. So, for example, if you have x to the -3rd power, a lot of you know that it's 1 over x cubed. That's not what this means. All right. So with that said, I just used both of these terms just so you could see it done this way and that way. And I've just abbreviated that way. So what does arcsin mean? It means what, so let's just pick a specific value. So arcsin 1, this means which angle has a sine of 1. So let's look at this diagram. If you want to have a y coordinate of 1, which is sine x, then you want to be over here. So this would be pi over 2. In other words, here we are saying if you plug in an angle, what's the value? And here we're asking the reverse question. We're saying if this is the value, what's the angle that gets you that value? So these are called inverse functions. And I want to make a pretty key point here, which is some of you might know this, some of you don't. If you don't, this will be very helpful. If you take f, which is a function of the inverse, you get x. So what does that mean for our purposes? If you have anything like that, let's say, some function, here's the y equals x line, here is the mirror image, let's say, I don't know, that's roughly my mirror image. That means if you put this function into the inverse function, then the output is just x. So you'll see how we're going to use this. So there's kind of two ways to do this. One is thinking it through like we did, and the other half of it is using this trig. So we know what sine x looks like. That's going to look like that. If we want to find arcsine of x, or sine inverse of x, we can just cheat, and what we're going to do is reflect this across the y equals x line. So that's using this fact. If you don't, I'm just giving you a little bit of foundation. So if you just want to figure this out, you might just want to think about, just think of the reflection in this line and maybe don't worry about so much of that. But that's where this idea is based in. All right. So if we have, this is our regular sine function and we want to plot arcsine of x. I'm going to combine this idea of the reflection with just looking at our unit circle. So to consider the arcsine function, we're going to restrict ourselves to the interesting regions, which is the value of sine of x can only be between -1 and 1, because the height on the unit circle can only range between -1 and 1. So that's why we have this domain here. And then what's the output? Well, let's see. I'm just going to think of it this way. So in other words, if you go down -pi over 2, you get the minimum height, and if you go up pi over 2, you get the maximum. So that's why I've chosen these as our sort of window to look at it. So let's see, if you plug in -90 degrees, you get -1. So in other words, which angle gives you a value of -1? Well, that would be right here. All right, so now let's see, which angle gives you a value of +1? So if you want to have +1, you would want to go over here to 90 degrees. All right, so what about 0? So if you want to be at 0, well, then you can plug in 0 degrees. So that tells us we're over here. So now it's a matter of figuring out, does this curve go this way or does it go this way? Because we already have an intuition from all these trig functions. They're not linear, they're kind of crazy. So a pretty good guess is it's either this way or that way. Now to do that portion of it, rather than to go into detail, that's where I'm going to use the second fact of just reflecting things across this y equals x line. Because we already know the sine function, which curves at first that way, that I'm going to cheat, and so for that I'm going to say that this is going to curve this way. Okay, so using this reflection idea, because the regular sine curve goes like this, so let me just make it a little larger so you guys can see. We're going to take the opposite of this reflected in the y equals x line, and I'll draw this in a different color. So that tells us it's this way. So that's how I knew this one was going like this. And so since this is going this way, we can use the same logic and reverse this portion to go that way, because it's reflected across the y equals x line. So like I said, we're piecing together two pieces of information, just using our brains with these critical points and using this y equals x idea to get the curvature right. All right, so that's it. I'm not going to go through each of those. I encourage you, if you want to figure out one of these, use the same process we've done. Get your critical points, figure out the curvature, trace through what we did for the other ones, and the rest of them should make sense. If they don't, feel free to ask questions. All right, so now we're going to move on to transformations. Okay, so here's the idea. for a lot of you guys are probably interested in specific examples and how to do homework problems or whatever. So this f is just a general function. This could be sine of x, cosine of x, any one of these. So you basically, for most of these problems, you're going to have four things going on: a, b, c, and d. So those are the things that, now these could be negative, fractions, whatever, but you're going to have four numbers. So we're going to go over one example. I'm not going to go over every type of example, but from this one example, you'll be able to understand how each of these numbers works. Now, a few key terms: amplitude, period, and phase. Don't focus on these terms too much. I'm going to just focus on the numbers, but then I'll tell you, you might see these terms used, so you'll know what they're talking about. So let's go to this example, -2 sine of 2 theta minus pi over 3 plus 1. And we are going to systematically figure out from our basic sine function so that's our basic sine function. This is pi over 2. All right, so how do we mess with this till we get that? That's the idea. So we're using theta. It doesn't matter what variable you use. So this is our theta axis. This is our y. All right, so here's the idea. The easiest thing to see is this first number. So what is this -2 doing? Well, the negative part of it is going to flip everything. So that means this hump will be flipped negative. And if it's already negative, it will be flipped positive. Now, the amplitude refers to the magnitude of something. So usually our sine function is between -1 and 1. So in other words, this height from this baseline of 0 is just a height of 1. But that 2 means we're doubling everything. So think of it as like this is getting stretched. So first of all, we negated it. Now it's getting stretched, so it's going to look like that. So instead of going to 1, it'll go to 2 and -2. So that's what this first number, which is the amplitude. Think about like waves and swimming or surfing. That's what that -2 is doing. You just have larger waves. If this is a small number, you have smaller waves. And if you have a negative, it flips everything across the axis. All right, that's the first number. Then we have this second number, this b, or in our example here, 2. So that will affect the period. So what is the regular period? So let's draw a little sine function here. So normally a period is the distance from one peak to the next peak. So this is pi over 2. So you can calculate this. Basically, this will be 2 pi. So it's going to take 2, or you can go, because everything is nice and symmetric, you can just go from this point to this point, and that's a distance of 2 pi. So that means every time you go through 2 pi, you're going to get a repetition of the same thing. So that's the period. How long does it take for it to repeat? Now let's think what that 2 is doing. So let me clean this up a little bit. So we discussed that first -2. So we had this original function. Then we flipped it so that it's flipped and then amplified. So it's going to -2 and +2. And now we want to know what that 2 is doing. So let's think about that. Normally, if we have sine of x, that means that for us to go through one period, x is going to have to go from 0 to 2 pi, or 0 to 360 on the circle, then things repeat. But now, since we're doubling whatever we're putting in, it's going to do this twice as fast. So that means, let's say I plugged in 180 for that's my angle. I thought I'm at 180, but now I'm actually doubling 180, so now I'm already at 360. I'm at the end already. So normally, if I thought I was here, if I doubled it, I'm already here. So to get to the end, if I'm doubling my input, I only have to go halfway. So that tells us that our green curve, which is our current curve, after applying only the -2 transformation, will be condensed. So think like an accordion. So now this green curve will already reach this point over here. So it's going to look like that. So we took, and let me do that in a different color. So where we should have gotten to this point at 2 pi, we're going to get to this point at pi. So we condensed our accordion. Now, if this number is, let's say, half So then we would have to go twice as far just to get to 360. So then it would be stretched out. So that's what this number is doing. So that's affecting the period. Now let's go to this third number, the c, or in our case, pi over 3. So I'm just going to apply this to a normal function first, and then at the end we're going to apply everything together. So here's our normal sine function. This is pi. This is 2 pi. All right. Now, what does this mean? So let's just look at sine of x minus pi over 3 in isolation. Normally, if I want to get sine of 0, I just plug in x is 0 because that's my input. Now, if I want this to be a 0, how do I get this to be a 0? I have to put in pi over 3. So think of it like maybe weightlifting. This negative pi over 3 is hurting me, so I have to work pi over 3 harder just to get to 0. So therefore, this is going to have a left-right shift, but the common mistake is people always think minus is to the left, but here it's counterintuitive because this is affecting your input. So in other words, this isn't tacked on at the very end. This is saying you thought you plugged in an x, but psych, you actually plugged in x minus pi over 3. So to get to x, you have to go pi over 3 to the right. So this will look like that. It is moved to the right. If there's a plus sign here, it's moved to the left, because think of it like if it's really easy, you're making it easier for me. There's a wind blowing in my direction as I'm running. Since you're adding pi over 3, I don't have to work as hard. I could be at negative pi over 3. So basically focus on one point. This original point has moved over here. So that's what this number means. It means it moves pi over 3 to the right. Alright, so far we've covered the -2, which is the amplitude. The 2 is affecting the period. It's making it shorter. The pi over 3 is moving it to the right. And the +1, since it's tacked on at the very end, if this is a plus, it's moving it up. If this is a minus, it's moving it down. So that's not one of these. So the pi over 3 is affecting the phase of the wave. That's called the phase. And then the one that I don't have a name for it, that's just a constant at the end. So altogether, this is what it would look like. At first, we are going to reverse it. We are going to then amplify it. We are now going to move it pi over 3 to the right. So it's going to, pardon my messy diagram. So we move it to the right, and now we're going to move it up 1. So the final thing is going to look something like that. It's just shifted 1 up. All right. So I know that was a little crazy, messy. Apply each of these step by step. So if you have some crazy function like cosecant inverse or cosecant of with some crazy numbers, first figure out what this basic function looks like. So you're not going to want to use the sine x. You want to use your basic function, and then apply each of these transformations one by one. All right, I'll see you guys in the next video.